Okay, welcome. We shall learn about something called the method of partial fractions. First, a very quick warm-up problem. 3 over x plus 4 plus 2 over x minus 7. This is the kind of thing you did like in week 1 of Precalc A. So the task is, add those two rational expressions, and this is a sort of a unit on rational functions, so that's kind of why this is relevant. There is a method. The method is to get a common denominator, and so we do a little bit of that. And you just multiply that. Did you get this? 5x minus 13 over x plus 4, x minus 7. Yeah? Great. Okay, everyone's been doing that since middle school. Let's now do the reverse. The method of partial fractions just takes this process and does it in reverse. So here we go. Number 2. 4x plus 1 over x minus 2, x plus 5. Okay. For some obscure reason that I don't want to talk about right now, it is useful to be able to break this back up again into small pieces. In other words, undo this process. Okay, so what does that even mean? There's kind of a lot going on in partial fractions if you stop to think about it. What do I sort of want? Based on the characterization of this as just undoing what we just did, then the sort of thing that I want to do is kind of like break this up into some number of x minus 2's and some number of x plus 5's, yeah? Okay, well, someone's making an observation about something that like must be true about the numerator of this rational expression. What's your instinct? What kind of a thing is it? Everyone got really shy all of a sudden. What kind of a thing is it? Like a number. Yeah, like a number. Yeah, I think that this thing up here must be like a number. Maybe you were all thinking that and thought it was like too trivial to even say. And over here as well. And I think that's just true. Why? Billy?
Oh, I was going to say the vector thing, the addition of vectors.
What? I didn't hear what you said. Say it again.
It's the addition of vectors. Like if there's some combination of...
Yeah, kind of. I kind of know what you're talking about, but that's not a helpful comment right now. Wait, why do I know this is going to be an A and a B? Okay. I'll just tell you. I think you're thinking this. Everyone just got like, oh. Okay, I know this has to be a number because think about it. Well, there's two ways. There's like the kid response, which is, well, what else could it be besides a number? Well, it could be like some x's or something up there, right? But no, actually that can't happen because the next thing I'm going to do, if I was going to reverse the process, is to get a common denominator, and that would be multiplied by x plus 5 over x plus 5, yeah? But if there were x's in this numerator, then that would make like quadratic terms or higher. Follow along if you understand what I'm talking about. And same thing here. So then it just can't be. Okay, that is an answer. A maybe slightly better answer, more of a math teacher type answer is, if that numerator were some linear function, like, I don't know, 3x minus 7 or something over x minus 2, then that just can't be, right? It can't be that numerator was some linear function, because if it was a linear function, now the degree of the numerator would be greater than or equal to the degree of the denominator, and we could do polynomial long division. And if you did polynomial long division on this, I'm doing it in my head, it would be 3 minus 1 over x minus 2. I think I did that right. And that just isn't true, because there's just no free floating 3 just kind of over here on the right hand side, because there's no free floating 3 over here on the left hand side. So in other words, as long as you start with a rational expression in which the degree of the numerator is less than the degree of the denominator, which is indeed what we have, then so must each piece on the right-hand side also have that property, that the degree of the numerator is less than the degree of the denominator. Otherwise, you could just like divide and get like numbers and stuff. Okay, if you like that explanation, good. If you didn't, just like go with the flow. How do we actually do this now? Now that I've set it up, I think it's pretty obvious like what to do next, right? Just like solve this equation for a and b, more or less, right? And how are you going to do that? Yeah, just like get a common denominator and just like make it all happen. Yeah, exactly. Maybe a more, even a simpler thing is if we're getting a common denominator, really we just don't need these denominators at all, right? Because we're just going to equate the numerators. So I like to think of it as just multiplying through by x minus 2, x plus 5. So if you multiply through by x minus 2, x plus 5, then you get 4x plus 1 equals a x plus 5 plus b x minus 2. Agreed? Okay, and from here, just like do it. I don't even think I need to tell you anything else. Just like finish it up. Maybe that is where it's up. No, I don't know. Yes. And Keely is, no, you're not Keely. Here's something else, Keely. Is saying you can think of x plus 5 as like some vector, like 1, 5. And you can think of x minus 2 as some vector 1, negative 2 in some sort of space. And you're looking for linear combinations of those two vectors, which take you to 4, 1. That's like the deep answer to why that you know that this equation has a solution at all. Does that make sense to anyone? If not, if so, then cool. If not, then don't worry about it. But yeah, on some deep level, this is like the vector 1, 5, and this is like the vector 1, negative 2, and you're looking for linear combinations that give you...
Pardon the interruption. Can you send Anika to sign out?
Yes. Okay, so anyway, actually doing the problem I think is like pretty easy, yeah? I think I made a mistake and the numbers work out a little bit gross, but like, no fear. Here I just multiplied everything out. Is this what you guys did? And then, looking at the right-hand side, it's a polynomial. And the linear term of that polynomial is a plus b, and the constant term is 5a minus 2b. But if that equals 4x plus 1, then there's only one conclusion. It must be that a plus b is 4, and it must be that 5a minus 2b is 1. This is what you guys did? So that gives rise to a system of equations, and if I solve this system of equations, then I'll have what a and b are. So it's actually not so outlandish to think of this as a linear combination problem, because it really does turn into a system of equations. Okay, anyway, I gotta like do this now. 8. All right, so 7, 8, 9. So did you guys get 9 sevenths for A? Those of you who are like staying ahead of me. And if A is 9 sevenths, then B must be 19 sevenths. Ah, cool? Say cool. Okay, good. So what we have learned is that this rational expression, 4x plus 1 over x minus 2x plus 5, can be rewritten as 9 sevenths over x minus 2 plus 19 sevenths over x plus 5. Good? Alright, this is the simplest possible partial fractions problem. And I used to make a joke. I've been teaching this class for 10 years. Sometimes I joke at this point, like, and if you're an MCPS, that's all you do. And it turns out that's actually true. Like literally, we are 5% into this topic, but if you were in any other MCPS high school, that's all they ever do. Okay, but really we're just getting started because it gets way more complicated. So, look at the very next problem. Number 3, 3x squared plus 3x minus 4 over x minus 2, x squared plus x plus 1. Okay, what do you notice about this problem? What's up with that denominator now? Okay, no one wants to talk. What do you have to say about x squared plus x plus 1? It's like a quadratic and it sort of like doesn't factor, right? Yeah, good. Yeah, if you try to factor this, it just doesn't factor, man. So we call this an irreducible quadratic. And because this is an irreducible quadratic, we don't want to touch it or break it up into anything smaller. And therefore, the whole goal of this problem, I still haven't explained why I would ever want to do such a thing, but I'm not going to right now. The goal of this problem, therefore, is to break things up into like some number of x minus 2's and some number of x squared plus x plus 1's. Cool? Okay, well now, if we have absorbed the lesson of a few minutes ago, can someone tell me something about the form that this numerator over here must take? It will be a number again, yeah. This will be some kind of a number. And what about the numerator of x squared plus x plus 1? Yeah, this now, I should expect this numerator to be some sort of linear function. Again, there are two ways of thinking about that so that makes sort of sense. One is that if you were to go and get a common denominator again, you would multiply that a by this quadratic, so you're going to get like constant linear and quadratic terms. But over here, when you multiply, you're also going to get quadratic terms. And so that seems good. I guess the thing I'm trying to say is the reason why I should expect that this numerator is degree 1 or less is that it can't be degree 2 or higher, because if it were degree 2 or higher, when you multiply through by x minus 2, you get like cubic terms. You guys following this? But there just are no cubic terms up here in this numerator. That's the kid explanation. What I think is the deeper explanation is the degree of the numerator must be less than the degree of the denominator, because if not, I could do polynomial long division, and I can't, because I can't over here either, because quadratic over cubic. Cool? Okay, so you have to deeply understand the setup, and then you just have to do it, man, so go. Right, so are you just saying, how do you know that it's linear? You don't. It might turn out that b is 0. Yeah. If it turns out that b is 0, then the algebra will just tell you that, but you have to allow for the fact that it might not be. Yeah. So the best way to put it is it's linear or less. So we set it up as linear. Good. Thank you for asking that. Okay, you guys got that, yeah? And now is your strategy just to multiply everything out and combine all the like terms and all that kind of stuff? You did that already? Yeah. is you get something like this. I just set it up, multiplied both sides by the denominator, carefully distributed, recollected, and now I can look at both sides of this equation and observe that the quadratic terms have to match, the linear terms have to match, and the constant terms have to match. So a plus b has to be 3, a minus 2b plus c has to be 3 also, and a minus 2c is 4. Okay, so that is a system of equations, of 3 equations and 3 variables, and if I solve it, I'll be done. Who's with me? Okay, though that is nice and stuff, I don't want to actually do it this way, because this is like annoying. It's fine, and it's not wrong, it's totally right, and it will work, and it's completely okay. But there is a faster way, a little bit faster. And so I think this is worth learning, because it's just really faster, man. And so now, what I'm going to do is I'm going to kind of leave up everything I've done, but instead of actually solving the system of equations, I'm going to show you the faster way. Ready? The faster way takes it from this purple step here. So you still have to understand the partial fractions, and you still have to do the multiply through thing. But now, okay, so I'll just rewrite this line. 3x squared plus 3x minus 4 equals a x squared plus x plus 1 plus bx plus c x minus 2. Okay, now basically this is just an equation in which I have 3 sort of unknowns, a, b, and c. And so feel free to like solve for a, b, and c, like however you feel like, man. And one really fast way of figuring this out is just to plug in some numbers. What would be an extremely convenient number that I could plug into both sides of this equation, which would immediately cause lots of simplification? 0. Even better. How about 2? If you plug, so I'll just write when x equals 2, what do I get on the left-hand side? Well, I just plug 2 into this polynomial, I get 12, and 6 is 18 minus 4 is 14. But when I plug 2 into the right-hand side of this equation, this entire piece over here just dies, right? And in fact, what I get is 4 and 6 and 1 is 7a. Boom. Whoa. Whoa. A is just 2. So without having to solve this big old system of equations, I just immediately learned that a is 2. Good? Okay, and then other tricks are available. Some people mentioned that, well, here's one. One other trick is to look at the quadratic term. Now here, it's very clear that on the left-hand side of the equation, the coefficient of the quadratic term is 3. On the right-hand side, I claim for people of sufficient algebra skills, it's pretty easy to just like look at this and kind of know what the coefficient of the quadratic term will be. You sort of fake multiply it out, right? Here you're going to have an ax squared, and here you're going to have a bx squared, and like that's it, right? So here, I know that a plus b has to be 3, because on the right-hand side, I can just tell from just looking at it that the quadratic term is going to be a plus b. Sort of just a faster version of what we did when we multiplied it all out. Okay, well, if a is 2, then what's b? 1. 2 down, 1 to go. A nice number to plug in is just 0. So when x equals 0, what do you get? Well, on the left-hand side, you get negative 4. And on the right-hand side, you get a. If you set x equal to 0, you get a. And then you're going to get, plus c times negative 2. Ta-da! So 2c is a plus 4, but a is 2, so 2c is 6, so c is 3. Okay, so without having to actually solve a system of equations, just by like plugging in some cute little numbers here and there and doing a little bit of like algebra in your head, you can just like figure it out. Good? Okay, good. And it turned out, therefore, that this problem was 2 over x minus 2 plus x plus 3 over x squared plus x plus 1. And if you have time, you could always just multiply that back out and like double check that you did it correctly. Good? Say good. Okay, we're going to do one more problem before the bell rings, which is number 4. And this, everyone good with this? I'm going to erase it. 5, 4, 3, 2, yeah. Okay, so problem 4 is interesting. What makes problem 4 slightly interesting?
It has a square.
Yeah, there's like square, right? So there's like a linear, term, but it's like squared or something. Okay, so this is very subtle, and it's very, very hard to teach this correctly because it's hard to teach this correctly. So it's hard for me to explain to you what you're supposed to do here. So I'm going to try trying a new method starting this year. So our first approach to doing this problem is we are going to ignore the fact that this is a perfect square trinomial quadratic, and we're just going to treat it like it's a plain old boring quadratic. In other words, let's split this up into some number of x minus 2's plus some number of x squared minus 2x plus 1's. What I mean by that is let's temporarily pretend like there's nothing special going on here at all. Cool? Who say cool? Okay, and therefore, if that's how we do it, if that's how we think about this problem, then it's actually no different from what we did on the previous page, yeah? This number up here would have to be a, and here we should allow for the degree of the numerator to be 1 degree less, or possibly less than that. Okay, agree? Okay, good. All right, so now we can just start doing the problem. And I think it ends pretty quickly, so here we go. Here we're going to have a times, that's really like x minus 1 squared, right? Plus bx plus x minus 2. Okay, and now, how should we, is that right? Yeah. What seems like a good number you can just plug into this really fast? Yeah, how about just 2? All right. So when x is 2, on the left-hand side I get, 4 and 6 is 10 minus 8, I get 2. And on the right-hand side, when you plug 2 in here, this just 0 dies, and you end up with just A. Everyone good? Am I going too fast, or are we okay? That seems all right. Okay, good. So one variable down. What seems like another convenient number to plug in? Yeah, 1, I think you mean, right? Yeah. So how about when x is 1? When I plug in 1, what happens? On the left-hand side, I get 3. Is that true? Yeah. And on the right-hand side, I get, well now this term dies, and I get, what do I get? B plus C times -2 or something, right? Actually, I changed my mind. I think plugging in 1 is like not even really that helpful. Oh, maybe it is. Maybe I want the quadratic term. Let's do that. What's the x squared term? And here is a good way of practicing this. Can everyone just see, without having to actually multiply it out, that if I multiplied out the right-hand side, what would be the coefficient of the quadratic term? You're going to have an ax squared term, and you're going to have a bx squared term, right? So therefore, the quadratic term coefficient on the left, which is 1, on the right would have to be a plus b. Yeah? Say yeah. Therefore, since I already know that a is 2, b has to be -1. Agreed? Okay. And now maybe I'm just going to plug in 0. I don't know. maybe that's even easier than plugging in 1. If I plug in 0, I get 6 on the left, and on the right I get A, and I get negative 2C. Agree? Minus 2C. But A is just 2, so 6 is just 2 minus 2C, so 2C is negative 4. So I think I did something wrong. No, maybe not. So C is negative 2. Can someone back me up on that?
Yeah.
Okay, good. All right, so I'm seemingly done with this problem. But no, I'm not. Because here's what I've just learned. What I've just learned is, you guys are going to have to stay for like 1 minute after covering so I can finish this. What I just learned is that this is 2 over x minus 2 plus negative x minus 2 over x minus 1 squared. Okay, you could stop there. In theory, you could just stop there. But no, we don't stop there. Because we don't want to stop there, man. Because the whole point of partial fractions, and you're not really expected to understand this now, is to break things up as much as we possibly can. And so if I want to break things up as much as I possibly can, I claim that this can be broken up further. And we can break this up further by writing this as negative x minus 2 over x minus 1 all over x minus 1. Why would I do such a thing? Well, because x minus 2 over x minus 1, now I can do polynomial long division here. So let's do that really quick. Negative x minus 2, give me like 1 more minute. Divided by x minus 1, what do we get? It goes in negative 1 times, right? Say right?
Right.
So that's negative x plus 1. So that's minus 3. Right, so that's pretty easy. So the point of doing that is to observe that therefore I can rewrite everything that just happened in red as negative 1 minus 3 over x minus 1, but that's all over x minus 1. Cha. In other words, I just took the thing in red, did polynomial long division, and rewrote it. Right? Say right.
Right.
Okay, so then the real answer, in its most simplified form, is negative 1 over x minus 1 minus 3 over x minus 1 squared. And then there's this 2 over x minus 2. Who is following all this? Okay. Right? And you have to agree, because I just took the red, I did polynomial long division, and I just split it up into 2 terms, yeah? Okay, the point of all of this is that I am just telling you that for various reasons that I don't want to get into, this is preferred. Can you just agree with me that like aesthetically or something, this is like better? It's better than this. This thing here in green is not wrong, but this thing down here is just better because it's like more split up. And so, final small comment, in the future, when presented with this problem, x minus 1 squared, x minus 2, and knowing that this is always going to happen, we don't set it up like we did. In the future, we set it up as A plus B plus C. Knowing that, I will arrive at that point eventually. Because if I start like this, because I can sort of divide by one of them and split it up into like its number plus remainder and eventually end up here, then if the whole point is to end up here eventually, then it's faster to just set it up like that. Who's getting this? All right, good. I was a little bit rushed, I'm sorry. I will see you guys next week. I'm turning off the camera now.